The universe is constantly whispering to us in a language of light and radio waves. Some of these signals are so strange, so powerful, and so brief that they defy every explanation we can imagine. We are about to journey through 30 of the most baffling transmissions ever detected, from a single legendary pulse that screamed across space to mysterious bursts that repeat on a perfect cosmic clock. You will discover the wildest theories scientists have proposed, from exploding stars and ripples in spacetime to possibilities that stretch the very limits of imagination. What if a famous signal hailed not from aliens but from a kitchen appliance? Could a star's flickering light be evidence of a structure built by another civilization? By the end, you will have a front row seat to the greatest detective story in the cosmos, where every new signal rewrites what we think is possible. What do you believe is waiting for us in the cosmic static? It all began with a single sheet of computer printout paper. In the quiet of a summer night in 1977, a massive radio telescope at Ohio State University known as the Big Ear was silently sweeping the sky. It was listening for whispers from the cosmos, recording the steady hiss of background noise on a long roll of paper. Most nights, nothing unusual happened. But on August 15th, something extraordinary occurred. For exactly 72 seconds, the telescope's receiver locked onto a signal so intense, so perfectly tuned that it screamed above the cosmic static. It came from the direction of the constellation Sagittarius, and it vanished just as suddenly as it appeared. The next day, a volunteer astronomer named Jerry Amon was reviewing the data printouts, a routine task of scanning columns of letters and numbers. His eyes stopped on one particular sequence. The signal strength was recorded as 6EQUJ5. In the code the telescope used, letters represented signal intensities higher than the number 9. This sequence meant the signal had surged to a level 30 times louder than the background noise of deep space. Amon, stunned, circled the characters in red pen and wrote one word in the margin: "Wow." That single, powerful burst, now forever known as the WOW signal, was never heard again. Despite decades of searching the same patch of sky with far more sensitive equipment, the signal has remained utterly silent. This singular event made it the most famous and compelling candidate for an intentional extraterrestrial transmission in history. Why? Because it matched exactly what scientists predicted an alien beacon might look like: a narrowband signal at a specific frequency that natural cosmic objects simply do not produce. It was a perfect cosmic shout in a universe that usually only murmurs. The fact that it was never repeated only deepened the mystery, transforming it from a scientific anomaly into a cultural icon, a permanent question mark etched into our collective curiosity about who or what might be out there. For decades after that solitary WOW, astronomers chasing these cosmic flashes faced a frustrating reality. Every signal seemed to be a one-time event, a brilliant flash that vanished forever, leaving nothing to study but a fading memory in the data. It was like trying to solve a murder with only a single, blurry photograph of the crime scene. Then, in 2016, everything changed. A signal designated FRB 121102 shattered the mold completely. It was not a lonely shout into the void. It was a voice that decided to speak again. This fast radio burst, originating from a tiny dwarf galaxy, an almost unimaginable 3 billion light-years away, did the unthinkable. It repeated. That single fact transformed the entire field of study. Suddenly, these were not just cosmic firecrackers popping at random. Here was a source that could be watched, monitored, and revisited. The bursts themselves were breathtakingly powerful, each one a millisecond blast that released more energy than our sun does in 80 years. But the pattern or lack of one was the true puzzle. The repeater did not follow a neat schedule. It would fire off several bursts in quick succession, then fall silent for months. It was chaotic, unpredictable, and utterly mesmerizing. This irregular cadence ruled out simple explanations like a single collapsing star. Something was alive out there in that distant galaxy, something capable of generating these titanic energies over and over again on its own inscrutable timetable. The repeater had given scientists a permanent address in the cosmos, and with it, a profound new mystery. What kind of cosmic engine could possibly survive such repeated catastrophic blasts? Chaos, however, was not the only language these cosmic transmitters spoke. The next signal to captivate astronomers spoke in a rhythm of perfect, almost unnerving precision. Designated FRB 180916, this burst did not just repeat, it kept time. For 16.35 days, it followed an unbreakable cosmic schedule. For roughly 4 days, it would erupt with multiple bursts, a flurry of intense radio chatter. Then, as if a switch was flipped, it would fall completely silent for the next 12 days. This cycle repeated over and over, a metronome ticking across 500 million light-years of space. Its source was traced to a star-forming region in a nearby spiral galaxy, a relatively familiar cosmic neighborhood compared to the repeater in the dwarf galaxy. That clockwork regularity was a monumental clue. In the universe, true, perfect periodicity usually points to one thing: orbital motion. The leading theory envisions a dramatic cosmic dance. Imagine an incredibly dense, highly magnetized neutron star, the type we call a magnetar, locked in orbit with a massive companion star. As the magnetar travels along its elongated path, it might unleash its powerful bursts only during a specific phase, perhaps when it is closest to its companion and interacting with the star's intense wind. Alternatively, the companion star itself could act as a periodic shutter, its thick outer atmosphere blocking the bursts from our view for 12 days out of every cycle. Another compelling idea suggests the magnetar is not in a binary but is simply wobbling or precessing like a slowing top. As its magnetic poles slowly sweep across space, the beam of radiation it emits might only point toward Earth for a few days out of its 16-day wobble. This signal transformed the mystery from asking what could explode repeatedly to asking what kind of celestial machinery could possibly keep such perfect, predictable time. It was no longer a random siren in the dark. It was a lighthouse with a meticulously maintained beam, and its steady flash demanded a mechanical explanation. That perfect 16-day clockwork was a revelation, but every lighthouse needs its first keeper. The story of these mysterious bursts truly begins not with a repeater or a cosmic metronome, but with a single, lonely blip hiding in plain sight. Years before the WOW signal found its fame, another enigmatic pulse had already been recorded and forgotten. In 2001, a young astronomer named Duncan Lorimer and his student were sifting through old archival data from the Parkes Radio Telescope in Australia. They were looking for something else entirely: new pulsars, the steady ticking of dead stars. But buried in the observations from July 24, 1998, was an anomaly. A 5-millisecond spike of radio energy so powerful it saturated the telescope's receiver. This was the Lorimer burst, officially catalogued as FRB 010724, the very first fast radio burst ever identified, though no one knew it yet. Its significance was monumental, but its reception was initially one of profound skepticism. The signal was so intense and so brief that most astronomers who saw the data assumed it was not cosmic at all. It had to be terrestrial interference, they reasoned, a glitch from a passing satellite, a burst from a military radar, or even a microwave oven in the telescope's break room. The idea that a natural cosmic event could produce such a brilliant, fleeting flash from so far away seemed almost ludicrous. What ultimately convinced the scientific community was a single, crucial piece of evidence embedded within the burst itself: its dispersion measure. As the radio waves traveled across the vast, nearly empty space between galaxies, they interacted with sparse free electrons. Higher frequency waves travel slightly faster than lower ones. This meant the burst arrived at Earth not as a sharp click but as a descending chirp, the high notes arriving a fraction of a second before the low notes. The amount of that delay, the dispersion, was immense. It was far greater than anything a signal from within our own Milky Way could produce. The Lorimer burst had to have come from far beyond our galaxy, from a staggering distance of several billion light-years. That single data point transformed a dismissed glitch into the progenitor of an entire field of astronomy. It was the first undeniable evidence that the universe was capable of these spectacular, mysterious explosions, hiding in archives and waiting for someone to understand what they were seeing. While the Lorimer burst revealed a universe of explosive power, another signal from the same era whispered a different, more tantalizing possibility. In 2003, the SETI-at-Home project, which used the idle processing power of millions of personal computers worldwide to analyze telescope data, flagged something peculiar. A signal designated SHB-02+14 had been observed not once but 3 separate times. Its source was a seemingly empty point in the sky between the constellations Pisces and Aries. What made this faint whisper so compelling to those searching for extraterrestrial intelligence was not its strength, but its specific address on the radio dial. It was detected near the hydrogen line, a frequency of 1,420 MHz. Hydrogen is the most abundant element in the universe, and for decades, scientists had theorized that an advanced civilization might use this universal frequency as a logical channel for a cosmic beacon, a sort of interstellar calling card. Furthermore, the signal exhibited a slight drift, a change in frequency over time. This drift was consistent with what you would expect from a transmitter located on a planet orbiting a star, its motion causing a Doppler shift similar to the changing pitch of a passing ambulance siren. For a moment, it seemed to tick every box for an artificial signal. Yet SHB-02+14 was plagued by controversy. It was exceptionally weak, barely rising above the background noise. Critics argued it was likely just that random noise that had randomly aligned in a suggestive pattern, or perhaps a subtle technical artifact from Earth-based interference that the software had mistakenly clustered together. The fact that it was detected only 3 times in a vast dataset and never again despite follow-up observations cast a long shadow of doubt. It became the ultimate Rorschach test of the cosmos, a faint smudge on the data that believers saw as a potential hello and skeptics saw as the statistical ghost of wishful thinking. This persistent candidate, forever hovering on the edge of discovery, embodies the profound challenge of the search, separating the faint, hopeful signal from the immense and ever-present noise of the universe itself. The search for a whisper from the stars often leads us to the most familiar places, and in 2020 it led us right next door. Proxima Centauri, the closest star to our own sun, a faint red dwarf just over 4 light-years away, is known to host at least one rocky planet in its habitable zone. So when the Breakthrough Listen project detected a narrowband signal seemingly emanating from that very star, the scientific community held its breath. The signal, named Bale C1, was everything they had hoped for. It was a pure, persistent tone at 982 MHz, a frequency typically quiet on Earth because it is reserved for spacecraft communications. Most intriguingly, it exhibited a slight but steady drift, a slow shift in frequency over time that perfectly mimicked the expected motion of a transmitter located on a planet orbiting Proxima Centauri. For hours, as the Parkes telescope in Australia tracked the star, this candidate signal remained, appearing only when the telescope was pointed directly at our stellar neighbor and vanishing when it looked away. It felt, for a glorious moment, like the discovery of a lifetime, a call from the cosmic house next door. Yet, extraordinary claims demand extraordinary proof, and the investigation that followed was a masterclass in scientific skepticism. Researchers embarked on a months-long forensic analysis, scrutinizing every possible source of human-made interference. They examined local electronics, satellite passes, and even aircraft radar. The breakthrough came when they discovered the signal was actually present, though much fainter, when the telescope was pointed away from the star. It had been reflected into the data through a complex path of radio echoes, a ghost in the machine created by our own technology. The final, definitive blow came when they identified the signal's true origin. It was harmonically linked to a common oscillating clock used in everyday digital electronics, likely from a computer, a phone, or some other device near the observatory. BLC-1 was not a message from another world, it was a profound lesson from our own. It demonstrated the immense challenge of the search, proving that even our most promising detections must survive a gauntlet of scrutiny, where the most likely explanation is almost always a very human one. The silence from Proxima Centauri was a reminder that our greatest cosmic mysteries often wear the most ordinary disguises. Sometimes a signal is not a burst of radio energy, but the absence of light itself. This is the story of a star that began to behave in a way no one had ever seen. In 2015, data from the Kepler Space Telescope revealed a star about 1,500 light-years away, known as KSE 8462852, or Tabby's star, was doing something inexplicable. It was flickering, but these were not the gentle, rhythmic dimmings of a planet passing in front. These dips in brightness were chaotic, dramatic, and profoundly deep. The star's light would sometimes drop by a staggering 22%, a shadow far too vast to be cast by any planet. Imagine our own sun suddenly dimming by a fifth, a shadow so immense it could only be cast by an object larger than the star itself. The patterns were bizarre, with dips lasting for days or weeks with no regular schedule. It was as if enormous, misshapen shapes were drifting in front of the star in a slow, silent parade. In the search for an explanation, one theory captured the public imagination like no other. Could this be evidence of an alien megastructure? The idea was based on a concept by physicist Freeman Dyson, who speculated that a sufficiently advanced civilization might eventually build a vast swarm of energy-collecting satellites encircling its star, a Dyson sphere, to harness all of its power. The irregular, deep dimmings of Tabby's star seemed, for a thrilling moment, to fit the profile of a partially constructed swarm, blocking the starlight in random, jagged patterns. It was a breathtaking possibility, a cosmic engineering project on a scale beyond human comprehension. Yet, as scientists scrutinized the star across every wavelength of light, the megastructure hypothesis began to unravel. A key piece of evidence came from the way the star dimmed. An opaque solid object like a megastructure would block all wavelengths of light equally. But observations showed the star dimmed more in blue light than in red light. This is a classic signature of dust, tiny particles smaller than a grain of sand that scatter blue light more effectively. The leading theories now point to far more natural, though still exotic, explanations. The most compelling suggests a vast, uneven swarm of exocomets, icy bodies from the star's outer system that have been gravitationally disturbed, perhaps by a passing star, and are now spiraling inward in a catastrophic cloud, trailing enormous plumes of dust and debris. Another idea involves intrinsic stellar activity, with the star itself undergoing massive, irregular outbursts that throw up clouds of dark circumstellar dust. While the alien megastructure theory has faded, the true nature of Tabby's star remains an active and captivating puzzle. It taught us that the universe can send its signals not just in brilliant flashes of radio waves, but in the haunting, slow-motion dance of shadows, challenging us to look beyond our first, most exciting guesses to uncover a reality that is often stranger than fiction. The Galactic Center is a place of unimaginable violence and beauty, a crowded metropolis of stars swirling around a silent, gravitational monster. From this chaotic core of our own Milky Way, astronomers have detected a different kind of cosmic shout. These are the galactic center radio bursts, brief, powerful explosions of radio waves that seem to emanate from the direction of Sagittarius, a star, the supermassive black hole at the very heart of our galaxy. Unlike the distant repeaters we have discussed, these bursts are homegrown, originating from within our own cosmic neighborhood, yet their proximity does not make them any easier to understand. In fact, it makes the mystery even more profound. The bursts themselves have a unique fingerprint, a specific spectral shape or energy signature that distinguishes them from the fast radio bursts coming from other galaxies. Studying them, however, is like trying to listen to a whisper in the middle of a roaring hurricane. The galactic center is an incredibly dense and turbulent region, packed with swirling gas clouds, intense magnetic fields, and the frenetic energy of countless stars being born and dying. This environment acts like a thick cosmic fog, scattering and distorting radio waves as they travel toward us, making it extraordinarily difficult to pinpoint the exact source of any single burst. Is the signal coming from the immediate vicinity of the black hole, or from one of the many exotic objects orbiting it? The leading theories are as dramatic as the location itself. One strong candidate is a population of magnetars, those intensely magnetic neutron stars. In the dense stellar environment of the galactic center, magnetars could be pushed to their limits, their crusts cracking under immense magnetic strain and unleashing these powerful radio flares. Another possibility involves more ordinary pulsars, the lighthouses of dead stars, whose beams might occasionally sweep through a particularly turbulent patch of gas near the black hole, lighting it up in a brilliant, temporary flash. The most tantalizing theory, however, looks directly at the central beast. Could these bursts be the signature of asteroids or small planets being torn apart by the black hole's immense gravity? Or perhaps they are caused by magnetic reconnection events in the chaotic, hot plasma that swirls just outside the black hole's point of no return. Each burst from the galactic center is a cryptic message sent from the most extreme environment we can observe, a reminder that even at the heart of our own familiar galaxy, the universe is still writing its most bewildering rules. But the hunt for cosmic signals is a constant battle against false alarms, a lesson learned most memorably with a group of imposters known as perytons. For years, astronomers at the Parkes Radio Telescope in Australia had been detecting strange, fleeting bursts of radio waves. They looked, at first glance, remarkably similar to the distant fast radio bursts. They had the same brief, intense spike of energy, yet something was subtly off. These signals, named perytons after a mythical winged stag, always appeared during the daytime and only when the telescope was pointed low on the horizon. Most damningly, they showed a telltale frequency sweep, a dispersion that suggested they originated not billions of light years away, but right here in Earth's atmosphere. They were cosmic ghosts haunting the data, and their true identity became one of the most embarrassing and enlightening detective stories in modern astronomy. The mystery deepened until a young astronomer decided to test a hunch. He noticed the signals often appeared around lunchtime, so he began an experiment. He would open the door of the observatory's microwave oven while it was still running, and there it was. The instant the door latch released, a brilliant burst of radio noise flooded the telescope's receivers. The perytons were not messages from the edge of the universe. They were the sound of a hungry scientist interrupting his lunch. The microwave's magnetron, when the door opened prematurely, emitted a short, broadband pulse. This pulse would bounce off the observatory's metal walls and dish, finally entering the telescope's sensitive detectors from the side or from below, mimicking the signature of a celestial event. The discovery was a moment of profound humility. It proved that even our most advanced instruments are not immune to the quirks of human life. The perytons taught astronomers a crucial lesson about vigilance. They forced the development of new, stringent filters and verification protocols to distinguish true cosmic whispers from terrestrial clatter. It was a reminder that before we can listen to the stars, we must first learn to silence the noise of our own kitchens. The cosmic kitchen was finally quiet, its false alarms identified and filtered out. Yet the true signals kept arriving, not in lonely, sporadic whispers, but in a sudden, overwhelming flood. This deluge was made possible by a revolutionary new instrument in the mountains of British Columbia, Canada, called the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike traditional radio dishes that peer at a tiny patch of sky like a drinking straw, CHIME is a sprawling array of metal mesh cylinders with no moving parts. It acts as a colossal cosmic surveillance camera, staring at a vast strip of the sky overhead 24 hours a day. Its design is perfect for catching fleeting events, and when it began full operations, it changed everything. Almost overnight, the study of fast radio bursts transformed from a desperate search for rare anomalies into a thriving field of statistical astronomy. Where once a few dozen bursts were known, CHIME has now catalogued thousands. We are no longer listening for a single voice in the dark. We are hearing the roar of a cosmic crowd. This tidal wave of data has allowed scientists to do something remarkable. They have started to classify these bursts into distinct families. Some are one-off explosions, brilliant and solitary. Others are prolific repeaters, chattering away with their own unique personalities and cadences. This classification is the first step toward understanding what different cosmic engines are at work across the universe. But CHIME impact goes far beyond mere cataloging. Each burst carries within its dispersion a secret map of its journey. As the radio waves travel through the diffuse gas between galaxies, that slight delay tells astronomers exactly how much material they have passed through. By analyzing thousands of these bursts from all directions and distances, scientists are beginning to build a three-dimensional map of the universe's missing matter, the faint, invisible web of gas that theories said must exist but had never been fully seen. Perhaps most importantly, this flood of data has settled one of the biggest early debates. The sheer number of repeating bursts CHIME has found proves conclusively that these are not all catastrophic, one-time events like a single star exploding. The universe is filled with sources capable of firing off these immense energies again and again, surviving their own blasts. We are not witnessing cosmic deaths, but the persistent, often erratic heartbeat of extreme objects. The mystery is no longer if they exist, but how many different kinds are out there, each with its own story written in milliseconds of radio light. Deep within that same crowded, chaotic core of our own galaxy, another object defies every label we try to give it. Known as GCRTJ 1745-3009, this source near the galactic center emits a radio scream on a perfect, patient schedule. Every 77 minutes, like clockwork, it erupts. For roughly 5 minutes, it becomes one of the brightest radio objects in the entire sky. Then, just as suddenly, it shuts off completely, vanishing back into the background static for over an hour before its next performance. This is not the millisecond pop of a fast radio burst. It is a slow, deliberate flare, a cosmic lighthouse with an unusually long, steady flash. And what makes it truly baffling is that it does not fit the profile of any known cosmic engine. A typical pulsar, a spinning neutron star, would flash at us hundreds or thousands of times per second, not once every 77 minutes. A magnetar might produce giant flares, but they are unpredictable and violent, not this metronomic, gentle rise and fall. The rhythm is all wrong for the standard players, so what could possibly power such a strange, precise, and relatively slow heartbeat? One compelling theory points to a failed star, a brown dwarf. These are objects too massive to be planets, but not massive enough to ignite sustained nuclear fusion in their cores like a true star. Imagine a Jupiter-like giant, but dozens of times more massive. Some scientists propose that this particular brown dwarf could be incredibly magnetized. As it slowly rotates, its powerful magnetic field might interact with charged particles in its atmosphere or from a faint companion star, building up energy until it discharges in a bright, periodic radio burst. The 77-minute cycle could simply be its rotation period, a leisurely day on this strange world. Another idea involves a binary system, a dance between two objects. Perhaps a white dwarf or a neutron star is orbiting a cool, dim star. As they circle each other, their magnetic fields could connect and disconnect, funneling material and energy in a way that triggers a radio flare at the same point in every orbit. The 5-minute duration of the flare might be the time it takes for this magnetic link to form, reach a peak, and then break. GCRTJ 1745-3009 stands as a stark reminder that for all the categories we have created, the universe is still inventing new ones. It is a persistent, whispering clue that in the busiest district of our galaxy, there exists a class of object we have only just begun to notice, ticking away in the dark on its own patient, mysterious time. The patient heartbeat from our galaxy's core was a puzzle of timing, but the next signal delivered a shock of location. It came from a place where such violence was not supposed to happen. In early 2021, astronomers pinpointed the source of a repeating fast radio burst named FRB 202000120E, and its address was utterly bizarre. It was not in a turbulent, star-forming galaxy. It was inside a serene, ancient globular cluster orbiting the nearby Messier 81 galaxy. This was like finding a screaming newborn in a retirement home. Globular clusters are among the oldest structures in the universe, dense spherical swarms of millions of stars that formed over 10 billion years ago. Their stellar populations are ancient, quiet, and long past the drama of supernova. This single fact delivered a direct challenge to the leading theory for fast radio bursts. If these bursts are produced by young, highly magnetized neutron stars called magnetars, which are born in the violent collapse of massive stars, then they should be found where massive stars live and die. That means in the vibrant, dusty arms of spiral galaxies, surrounded by the gas and young stars of a stellar nursery. An ancient globular cluster where massive stars vanished billions of years ago should be a silent, magnetar-free zone. Yet the signal was unmistakably there, repeating its powerful blasts from this cosmic senior center. So what cosmic engine, forgotten by time, could still be operating in such a place? The answer may lie in the unique, crowded environment of the cluster itself. One compelling alternative points to a highly magnetized white dwarf. White dwarfs are the fading embers of sun-like stars, and in the dense core of a globular cluster, collisions or close encounters between them could create a rare, ultra-magnetic version. This object could potentially unleash bursts of energy as it accretes material or experiences magnetic reconnection. Another, more dramatic possibility involves the dead stars that do exist in these clusters, neutron stars. In the stellar traffic jam of a globular cluster's core, binary pairs of neutron stars could be nudged by passing stars into ever-tightening orbits, eventually spiraling together and merging in a cataclysm that produces a one-time burst. But for a repeater, the mechanism might be different. A neutron star could be in a tight orbit with a white dwarf or another neutron star, and their fierce gravitational and magnetic interaction could trigger repeated outbursts as material is stripped away and funneled by intense fields. This signal forces us to rewrite the story. It tells us that the universe can build the engines for these tremendous explosions not just in the fiery cradles of young stars, but also in the quiet, ancient cities of the cosmos where forgotten relics can still wake up and roar. While ancient clusters challenge our theories, other signals point to a hidden substance that shapes the entire cosmos. For decades, astronomers have known that something invisible holds galaxies together, a gravitational glue we call dark matter. It makes up over 80% of the universe's mass, yet it refuses to interact with light, making it utterly silent and invisible to our telescopes. But what if, in the faint static between the stars, we are finally hearing its whisper? This is the dark matter radio hypothesis, a radical idea that suggests some of the universe's unexplained, diffuse radio emissions are not from stars or gas at all, but the signature of dark matter itself. The theory proposes that dark matter particles, when they collide or decay, could produce bursts of energy, including radio waves. Specifically, scientists are listening for a faint, monochromatic radio line, a single, pure frequency broadcast across a galaxy or galaxy cluster. Unlike the messy, broad-spectrum radio noise from supernova or pulsars, this would be a sharp, clean signal with no natural astrophysical explanation. It would be the fingerprint of a specific particle, like the action or the sterile neutrino, converting into photons we can finally detect. Imagine tuning an old analog radio and suddenly, cutting through the hiss and crackle of distant stations, you hear a single, unwavering musical note. That is the kind of signal they are searching for, a tone that does not belong to any known instrument in the cosmic orchestra. Detecting such a signal would be a monumental dual discovery. In one stroke, it would not only identify the elusive particle that constitutes dark matter, solving one of the greatest mysteries in physics, but it would also explain the source of baffling, persistent radio halos seen around galaxies and clusters. We would go from mapping dark matter's shadow by its gravitational pull to actually hearing its voice, turning the universe's greatest ghost into a tangible presence speaking to us on the radio dial. The dark matter radio hypothesis searches for a pure, singular note in the cosmic static, but some of the universe's most powerful signals are born from a catastrophic symphony we can now see and hear. In August 2017, a new chapter in astronomy opened when detectors on Earth felt the fabric of spacetime itself ripple. The source was a collision of two neutron stars, the ultra-dense cores of dead suns, over 100 million light-years away. This gravitational wave event, followed moments later by a flash of gamma rays, triggered a global hunt across every telescope on Earth and in space. What they found was a kilonova, a brilliant afterglow of light across the spectrum, from gamma rays to radio waves. This was the electromagnetic signature of a neutron star merger, a known and now confirmed cosmic event. The collision forged heavy elements like gold and platinum in its fiery wake, painting the universe with the very stuff of jewelry and planets. This discovery provided a crucial contrast to the unexplained signals we have been exploring. For a time, scientists theorized that the one-off, non-repeating fast radio bursts might be the birth cries of these mergers, a final radio scream as the neutron stars spiraled together. The 2017 event showed us what a merger truly sounds like across the electromagnetic spectrum, and while it was spectacular, it was also a singular, fading firework. It produced a radio afterglow that lingered for weeks and months, not a millisecond spike. This fundamental difference in duration and behavior makes mergers an unlikely source for the repeating fast radio bursts. An event like FRB 121102, which has fired off hundreds of times, cannot be produced by a single, catastrophic collision. You cannot have multiple mergers in the same spot. The stars are gone. The kilonova discovery was a triumph because it explained one source of cosmic transience, but in doing so, it helped narrow the mystery for others. It told us that the repeaters, the cosmic metronomes, and the strange galactic heartbeats must be powered by something that can survive its own outburst, a persistent engine that lives to tell its tale again and again. That triumphant kilonova gave us a known cosmic engine, but its radio signature was a fading whisper. The true breakthrough for fast radio bursts arrived not from a distant collision, but from a known object right in our own galactic backyard. In April 2020, a highly magnetized neutron star named SGR 1935 +2154, a magnetar located about 30,000 light-years away in our Milky Way, woke up. It began firing off intense bursts of X-rays, a not uncommon tantrum for such a volatile object. But then, it did something unprecedented. On April 28th, amidst its X-ray flaring, it unleashed a millisecond radio burst of staggering power. For the first time ever, telescopes caught a fast radio burst in the act, and they saw exactly what produced it. This was not just a radio signal, it was a dual scream across the electromagnetic spectrum. The event began with a sharp X-ray spike, a crack in the star's immensely strained crust. A fraction of a second later, a brilliant millisecond blast of radio waves erupted from the same precise location. That radio burst, if seen from another galaxy, would have been indistinguishable from the mysterious cosmic fast radio bursts we have been detecting for years. This was the smoking gun. For the first time, astronomers had direct, undeniable proof that at least some fast radio bursts are generated by magnetars. The mechanism is thought to be a starquake. Picture the magnetar's crust, a rigid shell of iron under unimaginable pressure, locked in a battle with an interior magnetic field trillions of times stronger than Earth. When the magnetic stress becomes too great, the crust snaps, causing a seismic starquake. This sudden fracture shakes the magnetic field lines anchored to the star's surface, launching a storm of particles and energy that ripples outward, producing the X-ray flash and, under the right conditions, a coherent beam of radio waves. The detection from SGR 1935 + 2154 was a monumental validation, solving a major piece of the puzzle. Yet it also opened a new, deeper question. Is this the only answer? Could every fast radio burst in the universe, from the distant repeater to the perfect cosmic metronome, be traced back to a magnetar's violent shudder? Or have we simply identified one prolific actor in a much larger cosmic cast? The sheer diversity of burst behaviors suggests the latter. The magnetar we observed produced a one-off burst, not the repeating patterns we see from other sources. This implies that while magnetars are certainly one powerful factory for these signals, the universe may have multiple blueprints for building a cosmic siren. That magnetar outburst gave us a proven cosmic engine, a single type of star capable of a radio scream. But decades before that discovery, astronomers had already solved another great radio mystery, one that provides the essential baseline for understanding all the others. This is the story of the cosmic lighthouse, the pulsar. The theory is elegant and well established. When a massive star explodes in a supernova, its core can collapse into a neutron star, a city-sized sphere so dense that a single teaspoon of its material would weigh 1 billion tons. This newborn star spins incredibly fast, sometimes hundreds of times per second, and possesses a magnetic field trillions of times stronger than Earth. Crucially, this magnetic field is often tilted, not aligned with the star's axis of rotation. As the star spins, this off-kilter magnetic field whips through space, accelerating charged particles to near light speed at its poles. These particles then shoot out in two narrow, focused beams of radio waves, one from each magnetic pole. From our distant vantage point, this creates the perfect cosmic lighthouse. Each time a beam sweeps across our line of sight, we see a flash. As the star rotates with impeccable regularity, those flashes arrive as a steady, metronomic pulse, hence the name pulsar. The Crab pulsar, for instance, flashes at us 30 times every single second, a precision that rivals the best atomic clocks on Earth. This model is a triumph of astrophysics, explaining thousands of steady, predictable signals. But it is precisely this understanding that makes the other signals on our list so profoundly strange. A classic pulsar is a model of cosmic order. The unexplained signals are agents of chaos or operate on a bizarre, different scale. They defy the lighthouse model in 3 key ways. First, their periodicity is all wrong. A signal like GCRTJ 1745-3009 flashes not every millisecond, but every 77 minutes, a rhythm far too slow for a typical spinning neutron star. Second, their repetition is erratic. The famous repeater FRB 121102 fires off in unpredictable clusters, not a steady tick, and third, their energy is staggering. A single millisecond fast radio burst can outshine an entire galaxy of pulsars. The lighthouse model gives us the rulebook, a clear picture of how a spinning, magnetized object should behave. The unexplained signals are the pages where that rulebook has been torn up, scribbled on, and set on fire, forcing us to ask what else, besides a simple spinning star, could possibly create such brilliant and bewildering flashes in the cosmic dark. The pulsar gave us a rulebook for cosmic lighthouses, but for decades, humanity has been listening for a signal that deliberately breaks all the rules. This grand search has a name, SETI, the search for extraterrestrial intelligence, and it is guided by a single, elegant formula that frames our cosmic loneliness. Conceived by astronomer Frank Drake in 1961, the Drake equation is not a calculation with one answer, but a structured way to think about the odds. It asks a cascade of questions. How many stars form in our galaxy each year? How many of those stars have planets? On how many of those planets could life arise? How often would that life become intelligent and communicative? And crucially, how long would such a civilization last before fading away? Each factor is a variable, a profound unknown. Plug in optimistic numbers and the galaxy might be buzzing with conversation. Use conservative estimates and we might be utterly alone. The equation's true power is not in giving an answer, but in defining the search. It tells us what to look for, a signal that is artificial, a technosignature. This is why every unexplained radio burst, from the WOW signal to the faint whispers flagged by SETI at home, is first run through an alien hypothesis filter. Could this be it? Could this be the product of a mind, and not just a mindless cosmic process? Modern SETI, supercharged by projects like Breakthrough Listen, has moved far beyond listening for simple greetings. It uses the world's most powerful telescopes to sift through petabytes of data, hunting for the faintest needle in a cosmic haystack. The search now looks for specific technosignatures, a narrowband radio signal that stays locked to one frequency like a perfectly tuned car radio, something nature almost never does. It scans for powerful, pulsed laser flashes that could be used for interstellar communication. It even looks for evidence of giant structures, like the hypothetical Dyson spheres that might surround a star, by analyzing the infrared heat they would waste. Every time a new, unexplained flash or flicker is discovered, this filter is the first one it passes through. The initial, thrilling question is always the same. Is this finally evidence that we are not the only ones asking these questions? Most of the time, the answer is no, leading us to a new and fascinating natural phenomenon. But that filter must always be applied, because the discovery of even one true technosignature would be the most profound in human history, rewriting our place in the cosmos with a single, intelligently crafted pulse. The search for a mind behind the signal leads us to the very fabric of reality, to a theory so profound it suggests the universe itself might be ringing like a snapped guitar string. This idea moves beyond stars and black holes to the fundamental architecture of spacetime. In the first chaotic moments after the Big Bang, as the universe cooled and expanded, physicists theorized that defects could have formed in the structure of reality itself. Think of it like water freezing into ice. As it transitions, cracks and imperfections can form in the crystal. In the cooling universe, one possible imperfection is a cosmic string, an unimaginably thin, infinitely long filament of pure energy, thinner than a proton but with the mass of a mountain range packed into every inch. These are not objects in space, they are flaws in spacetime, one-dimensional cracks in the cosmic foundation. And if they exist, they would be under immense tension, vibrating and whipping through the cosmos at near light speed. The theory proposes that when two segments of a string cross, or when a loop of string pinches off and snaps, the event would release a titanic burst of energy, shaking the very fabric of the universe. That convulsion could theoretically produce a shock wave of radiation, including a brilliant, fleeting flash of radio waves that we would detect as a fast radio burst. The energy scales match perfectly. These theoretical snaps could easily account for the most powerful bursts we see. What makes this idea so compelling is its elegant connection to the earliest moments of everything. A signal from a cosmic string would not be a message from another civilization or even from a dying star. It would be a direct echo of creation, a fossil from the universe's first second of existence, finally reaching us billions of years later. It is a reminder that our greatest cosmic mysteries might not be written by aliens or stars, but etched into the fundamental code of reality, waiting for the right moment to resonate across the cosmos. Cosmic strings offer a glimpse into creation's first moments, but even the most mysterious signals can become powerful scientific tools. This brings us to a remarkable twist in the story of fast radio bursts. While we hunt for their source, these fleeting flashes are already giving us an unprecedented map of the universe's hidden architecture. Each burst acts as a cosmic yardstick, a brilliant probe fired through the dark spaces between galaxies. The key is in that characteristic chirp, the descending tone where high frequencies arrive before low ones. This dispersion is not a flaw, it is a measurement. The amount of that delay is directly proportional to the number of free electrons the radio waves have encountered on their billion light-year journey. Think of it like driving through fog. The thicker the fog, the more your headlights are scattered and dimmed. An FRB's dispersion tells us the total density of the fog it traveled through, the diffuse, ionized gas that fills the vast intergalactic medium. This is the universe's missing baryonic matter. For years, cosmological models told us there should be a certain amount of ordinary atoms, protons and neutrons, spread between galaxies, but a huge portion of it was simply invisible to our telescopes. It is too hot and too thin to glow in any recognizable way. Fast radio bursts are finally allowing us to weigh it. By analyzing thousands of bursts from different distances and directions, astronomers can build a three-dimensional census of this elusive material. Each burst is like a single flash of lightning in a distant storm. By measuring how that flash is dimmed and smeared, we can calculate the humidity and thickness of the entire atmosphere it passed through. The early results from this technique are profound. They confirm that the missing matter is indeed out there, woven into the cosmic web just as the models predicted. We are no longer just chasing phantoms. We are using their own brilliant echoes to illuminate the dark, empty spaces and prove they are not empty at all. That map of the cosmic web, built from brilliant flashes, shows us how far our reach has grown. Yet sometimes the most compelling signals come from startlingly close to home, from stars that could almost be our sun's twin. In 2015, the Ratan 600 radio telescope in Russia detected a powerful, intriguing signal. It came from the direction of a star named HD 164595, located a mere 95 light-years away. For a moment, the discovery sent a ripple of excitement through the scientific community. Here was a sun-like star, slightly older and a bit brighter than our own, and from its general direction came a strong, narrowband radio spike. The signal's characteristics were exactly what SETI scientists look for, a focused, non-natural radio whisper. The star was even known to have at least one Neptune-sized planet, adding to the tantalizing possibility. Could this be a beacon? The math was dizzying. For the signal to be an isotropic broadcast aimed in all directions equally, the civilization behind it would need to harness energy equivalent to the total output of its entire star, a Kardashev Type II civilization. If, however, it was a narrow beam deliberately pointed at Earth, the power requirement dropped to something still immense, but conceivably within the reach of a very advanced society. The brief flare of hope, however, was quickly tempered by cold, hard scrutiny. When other major radio telescopes, like the Allen Telescope Array in California, turned to stare at HD 164595, they heard nothing. The signal was gone. This silence was the first major clue that the source was not celestial. The most plausible explanation turned out to be frustratingly terrestrial. The signal's frequency matched a band commonly used by military and surveillance satellites. Investigators concluded that the most likely culprit was a secret Russian military satellite, passing through the telescope's field of view and reflecting its transmission off the ground or a building, creating a brief, misleading echo from the stars. HD 164595 stands as a perfect case study in the modern search. It had all the hallmarks of a dream discovery, a strong signal from a familiar star at the perfect frequency. Yet it vanished under follow-up observation, its origin traced not to another mind, but to our own planet's hidden orbital infrastructure. It is a humbling reminder that our sky is now filled with our own technological chatter, and every potential hello must first survive the gauntlet of proving it is not just a secret human good by bouncing back to us from the void. While we chase brilliant flashes and distant beacons, the universe also hums a quieter, more pervasive song. Drifting through the spiral arms of our own galaxy is a faint, mysterious hiss in the microwave part of the spectrum. For years, this anomalous microwave emission, or AIM, baffled astronomers. It was a diffuse glow that could not be explained by any known process. It wasn't the thermal warmth of cold dust, and it wasn't the synchrotron radiation from electrons spiraling in magnetic fields. It was something entirely new, a signature with no clear author. The key to unlocking it lay in thinking incredibly small. The leading theory now points to nanoparticles, specks of carbon or other materials smaller than a virus, floating in the vast spaces between stars. These are not just static motes of dust, they are thought to be spinning and spinning incredibly fast, billions of times per second. This furious rotation happens because they are asymmetric, shaped like tiny rods or disks. When interstellar ultraviolet light strikes them, it imparts a tiny amount of angular momentum, setting them into a wild, dizzying spin. And a spinning electric dipole, even one as small as a molecule, emits radiation. In this case, the radiation comes out as a faint microwave whisper, a collective hum from countless trillions of these microscopic cosmic tops. Solving the mystery of AIM did more than just label a strange signal. It revealed an entire hidden population within the interstellar medium. We now understand that space is not just filled with gas and large dust grains, but also with this fine, spinning nanodust. This material plays a crucial role in the chemistry of galaxies, providing surfaces for molecules to form and influencing how heat is distributed in star-forming clouds. What was once an annoying, unexplained noise in our data is now a vital tool for mapping the intricate and delicate ecology of our galaxy, reminding us that sometimes the most profound discoveries are not in the loudest shouts, but in learning to understand the universe's steady, whispering breath. But a signal's journey can twist and distort in ways that create a bizarre acoustic fingerprint. Some repeating fast radio bursts perform a strange little trick as they erupt, a phenomenon astronomers call the sad trombone or boomerang effect. Within the span of a single millisecond burst, the frequency of the radio waves does not stay constant. It drifts steadily downward, starting at a higher pitch and sliding to a lower one, like a cosmic slide whistle being played in reverse. This is not the dispersion caused by the long journey through intergalactic space, which affects the entire burst. This is a subtle shift happening at the source itself, or in its immediate, violent neighborhood. This tiny detail is a massive clue. It tells us that whatever is creating these bursts is not a simple, static click. It is a dynamic event unfolding at incredible speed. One compelling explanation involves the birthplace of the burst. Imagine the signal originates deep within a dense, magnetized cloud of plasma surrounding the source, perhaps the remnant of a supernova or a wind from the central neutron star. As the radio waves race outward from their point of origin, they must fight their way through this turbulent shroud. higher frequency radio waves can punch through the plasma more easily and escape first. The lower frequencies get slightly delayed, trapped and scattered by the dense cloud for a fraction of a millisecond longer before they finally break free. What we receive, then, is a staggered arrival, creating that descending chirp within the burst itself. Another idea turns this picture inside out. Perhaps the emission mechanism is moving. Picture a shockwave or a blast of energy rocketing outward from the magnetar's surface. If this wavefront is traveling through a region where the density of plasma decreases with distance, the part of the shock that emits radio waves could be born at a high frequency, and then, as it expands into thinner material, its emission frequency naturally drops. It is like listening to a siren on a speeding fire truck, but instead of the Doppler shift from motion, the siren's own inherent pitch is changing as it moves through different environments. This boomerang effect transforms each burst from a simple blip into a miniature sonogram of the source's immediate surroundings. By analyzing that slide, scientists can begin to map the invisible, seething storms of magnetized plasma that must envelop these cosmic powerhouses, hearing the shape of the storm in every fleeting note. We have listened for whispers and decoded the universe's strange songs, but in one historic moment, humanity decided to speak. In 1974, from the colossal Arecibo radio telescope in Puerto Rico, scientists broadcast our first deliberate message into the cosmos. It was not a random signal, but a carefully crafted pictogram encoded in binary. A series of ones and zeros beamed toward the M13 globular cluster, a dense ball of stars 25,000 light-years away. The message itself was a snapshot of who we are. It depicted a stick figure of a human, the double helix structure of our DNA, a diagram of our solar system with Earth offset to highlight its importance, and even a representation of the Arecibo telescope itself. It was a cosmic postcard, a shout into the void announcing, "We are here and we are curious." This act, known as active SETI or METI, messaging extraterrestrial intelligence, stands in stark contrast to the passive listening that defines most of our search. It flips the script entirely. Instead of waiting for a signal, we are sending one, initiating a conversation that would take 50,000 years for a simple round-trip reply. And this proactive step ignites one of the most heated debates in science. Proponents argue it is a natural, even noble, extension of our curiosity. If everyone in the galaxy is only listening, they say, the universe will remain forever silent. Someone must make the first call. They see it as a gesture of hope, a declaration that we wish to join a galactic community. The risks, however, are profound and chilling. Critics, including visionary thinkers like Stephen Hawking, warned it could be catastrophically naive. They compare it to the arrival of Europeans in the Americas, a meeting where the less advanced civilization suffered immensely. If a technologically superior species received our message and decided to visit, their motives might be beyond our understanding or control. They might seek resources or see us as inconsequential. The dark forest hypothesis suggests the cosmos is a dangerous place where advanced civilizations stay hidden to avoid predation, and our broadcast is like lighting a bonfire in that dark forest, announcing our presence to any hunters that might be listening. The Arecibo message was a symbolic gesture, its target so distant we will never see a reply. But modern METI proposals aim at closer, more promising stars, making the ethical dilemma immediate and urgent. Do we have the right, on behalf of all humanity and all future generations, to take such a risk? Or is our greatest wisdom found not in shouting, but in listening intently to the mysterious static, learning the universe's rules before we dare to introduce ourselves? Our own star, the Sun, is the loudest radio broadcaster in our solar system. Its constant activity creates a storm of noise that can drown out the faint whispers from deep space, and its influence stretches far beyond the orbit of Pluto. This vast sphere of the Sun's influence, the heliosphere, is shaped by the relentless solar wind, a stream of charged particles racing outward at over 1,000,000 miles per hour. But the sun's rotation twists this wind into a colossal, spiraling pattern known as the Parker spiral. Imagine a spinning lawn sprinkler with water streams curving out in an ever-widening spiral. The sun does this with its magnetic field, flinging it outward in a giant, whirling arch that fills the entire solar system. This spiraling magnetic structure is not a quiet highway. It is a turbulent zone of intense energy. When the solar wind interacts with planets, comets, or even itself, it can generate bursts of radio waves. These natural emissions can mimic the chirps and pulses astronomers search for, creating convincing cosmic ghosts in the data. A sudden solar flare or a coronal mass ejection can send a shock wave rippling through the Parker spiral, scattering and amplifying human-made radio signals from satellites and Earth, bouncing them back to our telescopes in distorted, time-delayed echoes that look for all the world like they came from the stars. This solar interference is a constant, formidable challenge. It means that every potential signal from beyond must first be vetted against the sun's daily tantrums. This is where space weather forecasting becomes as crucial to an astronomer as checking the clouds is to a stargazer. Teams monitor solar observatories around the clock, tracking sunspots, flares, and particle streams. Before a sensitive observation begins, they consult forecasts to avoid periods of high solar activity. Sophisticated software models the expected radio noise from the Parker spiral and subtracts it from the incoming data, a digital filter straining to separate the universe's true voice from the overwhelming roar of our own parent star. It is a daily reminder that to hear the cosmos, we must first learn to silence the sun. Our sun's roar is a local disturbance, but to find the universe's most powerful engines, we must look to its darkest hearts. The black hole jet theory proposes that some of those brilliant fast radio bursts are not the cries of magnetars, but the death screams of matter falling into oblivion. Picture a stellar mass black hole or a neutron star locked in a fatal embrace with a companion star. Its immense gravity is a relentless thief, stripping gas from its neighbor and pulling that material into a swirling, superheated disk. As this plasma spirals inward at nearly the speed of light, it doesn't all vanish. Intense magnetic fields channel some of it away from the poles, launching twin jets of particles moving at over 99% the speed of light. These jets are cosmic blowtorches stretching for light years and glowing across the electromagnetic spectrum. Within these jets, theorists suggest, could lie the secret of the fast radio burst. One possibility is magnetic reconnection. The jet is not a smooth river, it is a chaotic, magnetized maelstrom. Opposing magnetic field lines can snap and violently reconnect, like rubber bands breaking and lashing together, converting magnetic energy directly into a storm of radiation and particle acceleration. This sudden release could, under the right conditions, produce a tightly focused beam of coherent radio waves, a millisecond spike of pure power. Another mechanism involves internal shocks. If the black hole's feeding is messy and erratic, it might belch out material in clumps. A faster-moving clump could slam into a slower one ahead of it deep inside the jet. That collision would be a titanic shockwave, a cosmic traffic jam at relativistic speeds, and the resulting energy could be funneled into a brilliant radio flash. This model offers a compelling alternative to the magnetar starquake. It shifts the source from a solitary, quaking star to a binary system, a dynamic duo engaged in a violent transfer of mass and energy. So how could we tell the difference? The clues are in the details. A burst from a jet might come with a distinct entourage. It could be preceded or followed by other forms of high-energy radiation, like X-rays or gamma rays, signaling the violent accretion process. The burst itself might show a specific polarization pattern, a twist in its radio waves caused by the ordered magnetic fields within the jet. And if the source is a repeating burst, its pattern might be tied to the orbital dance of the binary system, or to the flickering, unstable rhythm of the black hole's feeding habits. The black hole jet theory expands the cosmic stage, reminding us that the universe has more than one way to scream. It suggests that sometimes the brightest flash in the dark is not a star's final tremor, but the focused beam of a gravitational monster's last meal. That solitary, perfect shout from 1977 has never been matched, but in 2017, a new explanation emerged that promised to solve the mystery with a surprisingly mundane culprit. Astronomer Antonio Paris proposed that the WOW signal was not a beacon from the stars, but a cosmic reflection from our own solar system. His hypothesis centered on two comets, 266P Christensen and 335P Gibbs. These icy wanderers, unknown at the time of the original detection, were passing through the exact region of space the Big Ear telescope was monitoring. Comets are surrounded by vast clouds of hydrogen gas, released as solar radiation vaporizes their icy nuclei. As Paris explained, a radio telescope tuned to the hydrogen line could theoretically pick up this amplified hydrogen emission if a comet passed directly through its field of view. The signal would be strong, narrowband, and would appear and disappear as the comet moved, neatly matching the WOW signal's 72-second duration and subsequent silence. It was an elegant, natural solution that would demote the most famous candidate for an alien message to a simple celestial weather report. Yet, the astronomical community greeted the idea with deep and widespread skepticism. The problems were fundamental. First, and most critically, researchers checking the published orbital data found that comet 266P Christensen was likely not in the right part of the sky on that August night. Its position was off by a significant margin, placing it outside the Big Ear's two very narrow receiver beams. Second, the signal's intensity was staggering, 30 times the background noise of deep space. Cometary hydrogen clouds are diffuse, and no other comet before or since has ever produced a radio burst even remotely that powerful. Third, the signal's profile was too perfect. It rose to a sharp peak and fell away cleanly, whereas a signal from a moving, irregular cloud would likely show more variation and distortion. While the comet hypothesis was a creative and testable idea, it ultimately failed to align with the evidence. The WOW signal retains its unique, pristine power precisely because every attempt to explain it naturally has fallen short. It remains the universe's most brilliant unanswered call, a 72-second masterpiece of mystery that continues to defy our attempts to write it off as anything less than extraordinary. The universe sends its messages through more than just light. To truly understand the violent engines behind these radio screams, astronomers have opened new ears on the cosmos, listening for the faintest ghosts of matter and ripples in spacetime itself. This is multi-messenger astronomy, a coordinated hunt that looks for different signals from the same cataclysm. Alongside the brilliant flash of a fast radio burst, scientists desperately search for two other cosmic messengers, high-energy neutrinos and gravitational waves. A neutrino is a fundamental particle so ghostly it can pass through a light year of lead without a whisper. They are born in the most extreme environments, like the hearts of collapsing stars or the disks around black holes. If a powerful neutrino detector on Earth, like the Ice Cube Observatory buried in the Antarctic ice, recorded a neutrino burst at the exact moment a distant fast radio burst went off, it would be a revolutionary clue. That coincidence would scream that the source was a truly catastrophic event, something like a neutron-star merger or a black hole being born, where unimaginable pressures shred matter and create a firestorm of these elusive particles. Similarly, the Laser Interferometer Gravitational Wave Observatory, LIGO, listens for the faint shudders in spacetime caused by massive objects colliding. A gravitational wave chirp arriving in tandem with a fast radio burst would be the ultimate confirmation of a merger. Yet, despite years of careful searching and rapid alerts that swing telescopes around the world toward new bursts, that definitive match has not been found. The neutrinos and the gravitational waves have not shown up to the party. This profound silence is itself a deafening piece of evidence. It tells us that the most popular repeating bursts are likely not coming from the single, universe-shaking collisions that would produce such powerful secondary signals. The non-detections gently but firmly push the needle toward sources that are destructive, but not utterly final. They point toward objects that survive their own outbursts, like the magnetars we have seen in our own galaxy. A magnetar starquake is titanic, but it is a local event on the star's crust, not a collision that annihilates entire stellar corpses and shakes the fabric of the cosmos. The empty silence from neutrino and gravitational wave detectors is helping to narrow the cosmic suspect list, suggesting that the universe's most common radio screams are the tantrums of immortal monsters, not their death cries. Every great mystery needs a moment where the line between science fiction and reality blurs completely. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a new radio telescope she had helped build in Cambridge. Scrolling through miles of paper chart recordings, she noticed a peculiar, repeating signal. It was a sharp, regular pulse arriving every 1.337 seconds with breathtaking precision, a cosmic metronome ticking away in the constellation Vulpecula. The signal was so unnervingly perfect that she and her supervisor, Anthony Hewish, half-jokingly labeled it LGM-1 for little green men. The possibility that it was an artificial beacon, a lighthouse built by another civilization, was seriously entertained. Here was the ultimate unexplained signal, a pulse so regular it seemed engineered. The discovery sent a ripple of profound excitement and anxiety through the small team. They quietly investigated, searching for any sign of modulation or a second signal that might carry a message. The truth, when it finally emerged, was no less extraordinary. They had not found little green men. They had discovered the first pulsar, CP1919, a rapidly spinning neutron star, the collapsed core of a dead sun. This natural cosmic lighthouse, with its immense gravity and magnetic fields, was the engine behind those perfect pulses. That moment of reclassification was a landmark in human thought. The LGM-1 signal moved instantly from the category of profound mystery to a cornerstone of understood astrophysics. It established a new class of celestial object and earned a Nobel Prize. This historical pivot is the essential backdrop for every strange signal we chase today. It teaches us a humbling and exhilarating lesson. The universe is capable of producing phenomena so precise, so seemingly artificial, that our first instinct is to see a mind behind them. The frontier of the unexplained is not a fixed wall. It is a horizon that retreats with every new discovery, transforming today's alien mystery into tomorrow's textbook fact, and reminding us that reality, when fully understood, is often more wondrous than our wildest speculations. The discovery of pulsars taught us that nature can mimic a perfect machine, but our current tools still hear only the loudest cosmic voices. To listen for the whispers, we need a telescope of impossible scale, and that future is already being built. Across the remote deserts of South Africa and the plains of Western Australia, a new kind of ear is taking shape, the Square Kilometre Array, or SCAR. When completed, it will not be a single dish but a vast, sprawling network of thousands of antennas, working in concert to create a single, colossal radio ear with a total collecting area of, as the name suggests, a square kilometre. Its sensitivity will be staggering, capable of detecting an airport radar on a planet orbiting a star tens of light years away. For the mystery of fast radio bursts, this changes everything. Where current telescopes catch a few thousand bursts, SKA will detect millions, turning rare anomalies into a rich statistical tapestry. It will not just hear the bursts, it will see them with pinpoint precision. Imagine tracing a single, brilliant flash not just to its host galaxy, but to the exact neighborhood within that galaxy, perhaps even to the specific star cluster or supernova remnant that birthed it. This level of localization is the key to unlocking their engines. If a burst is pinpointed to a known magnetar in a nearby galaxy, the case for that model becomes ironclad. If it is traced to a region devoid of young stars, it forces us to consider older, stranger engines like white dwarf mergers or cosmic strings. SKA will map the dispersion of each burst with exquisite detail, allowing us to weigh the missing matter in the cosmic web with unprecedented accuracy, turning each flash into a precise probe of the universe's hidden structure. And then there is the oldest, quietest hope. The same sensitivity that will find millions of bursts could also finally detect the faint, persistent hum of a technosignature. Our current searches are limited to powerful, deliberate beacons. SKA could potentially pick up the equivalent of our own everyday planetary leakage, the collective radio chatter of television broadcasts, radar, and satellite communications from a civilization like ours. It could hear the quiet background hum of another world's technology, a signal not meant for us but one that speaks volumes. This telescope is not just about building a bigger instrument, it is about opening a new sense. We are moving from glimpsing the occasional lightning bolt in the cosmic storm to hearing the entire symphony of the radio universe, from the faintest stellar rustle to the possibility of a distant technological murmur. The SKA promises to transform our deepest cosmic mysteries from questions of speculation into vast fields of data, where every strange signal will finally have a clear address, and every whisper will be given a chance to tell its story. The search for one single answer may be the most human instinct of all. We crave a neat equation, a universal law that neatly explains every brilliant flash and every haunting whisper from the dark. But the cosmos resists simplicity. After this journey through 30 of its most baffling signals, a different, more beautiful picture emerges. The universe is not a factory with one assembly line. It is a vibrant, chaotic zoo of cosmic engines, each capable of its own unique radio scream. The truth is not a single theory of everything. It is a symphony played by an entire orchestra of extreme physics. We have already identified several of the lead musicians. The magnetar is the volatile soloist, its crust cracking under magnetic strain to produce the sharp, powerful pops we have seen in our own galaxy and likely in many others. The black hole jet is the deep, resonant bass, funneling the death screams of accreted matter into focused beams of unbelievable power. The colliding neutron stars are the symbol crash, a single, catastrophic event that rings across the spectrum. And in the quiet corners, we may still have the exotic instruments, the theoretical players like snapping cosmic strings or annihilating dark matter, waiting for their moment to be heard. This diversity is not a failure of our understanding, it is the key to it. The perfect clockwork of a 16-day repeater tells a different story than the chaotic chatter of another. The ancient signal from a globular cluster points to a different engine than the youthful blast from a star-forming region. Each strange behavior, each unique fingerprint in the data, is a clue to the specific conditions that created it. To force them all into one box would be to miss the magnificent variety of the universe itself. And yes, in this vast cosmic zoo, we must still leave a cage empty, its door slightly ajar for the possibility of a signal born not of physics but of mind. The technosignature remains the most profound outlier, the one source that would rewrite every other exhibit. The search continues not because we expect to find it, but because we must be open to the universe surprising us in the most profound way imaginable. Our task now is not to find the answer, but to learn the language of this radio zoo, to understand the habits of each creature, and to appreciate the fact that the cosmos is far more creative and far more strange than we ever dared to dream. From the solitary, perfect shout of the WOW signal to the roaring crowd of thousands heard by chime, we have crossed a universe of mystery. Each of these 30 cosmic whispers and shouts, from the haunting shadows of Tabby's star to the patient heartbeat from the galactic core, represents a frontier of human curiosity. Some, like the perytons, were solved with a dash of humility, reminding us that the universe's greatest puzzles sometimes begin in our own kitchens. Others, like the magnetar connection, gave us a triumphant answer that only opened deeper questions. And many, from the eerie 16-day metronome to the ancient signal in a globular cluster, remain wide open, their true nature still hidden in the dark. This is not a story of unsolvable riddles. It is a testament to how each anomaly, each unexplained blip on a graph, forces us to invent new tools, conceive new physics, and push the boundaries of what we believe is possible. Our maps of the cosmos are drawn not just by what we understand, but by the brilliant, baffling landmarks we do not. So keep looking up, stay curious. The next great cosmic mystery might be hiding in plain sight, waiting for someone like you to notice a strange pattern, to ask a new question, or to build the instrument that finally hears the universe's quietest secret. What cosmic whisper captures your imagination the most? Share your favorite space mystery in the comments below, and if you enjoyed this journey through the static, be sure to subscribe. The universe is still talking, and the greatest chapters of this story have yet to be written.